Hello, everyone. I'm Adarsh. I'm a data scientist at Sophos AI. But more importantly, I want you to know that I was in the top 10 in the trivia contest today. That's right. But I guessed all the answers, so it doesn't really help my imposter syndrome. All right, I have my slides. So, before I begin my talk, uh, I'd like to mention that a lot of this work is a culmination of efforts from a lot of former and current members of Surface AI. So I'd like to thank them for their contributions here. All right, so what am I going to talk about today? I'm going to start with a little bit of background on large language models, and then let you know what models we picked to evaluate for our benchmarks, and then explain what each of our benchmark tasks are. Then I'm going to go through the results, the performance that we saw on our benchmark tasks, and then I'm going to conclude with takeaways. I have a lot of detailed results that we collected during all our experiments, and I won't have time to go through all of them. But to satisfy all the data nerds here, I have all my detailed results in the appendix, so you can dig through them at your leisure. Okay. So if you haven't heard of LLMs yet, let me give you a little bit of a background. Large language models are basically using something called a transformer architecture as the building blocks. They mostly operate on text, although there are some multimodal large language models, but I won't get into that. Under the hood, they use something called self-attention to learn long range and complex dependencies between different parts of the input text. And then they use their learned representations to generate new text token by token based on the input text that they're seeing. Okay. So even if you've been living under a rock for the past few months, you've probably heard of ChatGPT, how it's going to steal your job, and how it's going to steal the rock you're living under. So when you have so much hype, so much interest, and so many organizations getting involved, producing their own large language models, the waters get really murky when you're actually trying to apply some of them for your own tasks. One of the ways that you can figure out what model would work for your application is benchmarking. So we have the Hugging Face LLM leaderboard, which basically kind of runs some popular NLP benchmarks on all the open source LLM models that were submitted. But if you're looking for something that's security specific, as we found out, you're just out of luck. You have to make your own benchmarks, which is pretty much what we ended up doing. So for our experiments, we picked a few models to evaluate. Mostly our criteria was whether we have access to them, whether we can afford to run them, and finally, do we have enough context size? This was a big one. For some of our benchmarks, we needed a lot more context size, so we had to exclude a few models that had a context size limitation of like 2,000 tokens. So yeah, we picked a few models from OpenAI, from AI21 Labs, from Amazon, Meta. I'm sure a lot of these are household names for some of you at this point. So moving on to the benchmarks themselves, as I mentioned before, we came up with 3 benchmarks. I will explain them all in detail with examples. So the first one is basically, I'm calling it the natural language interface. It is to test the ability of a large language model to assist a threat analyst in threat hunting or investigation. So boiled down, this task is basically, I'm going to give you a natural language query. Can you convert that into SQL so that I can plug it into my system and sort of get information back get relevant information that I'm looking for back? So that's what the prompt looks like. So here's an example prompt. You start off with an instruction that says translate the following request into SQL. And then we provide the LLM with the schema information for the underlying data. This is just some synthetic data the tables that we created. And then finally, we set it up as a three-shot problem. So we give the LLM three request and SQL pairs, and then finally give it a fourth request for which it has to generate SQL. For this task, we had, so this is a pretty small prompt. We had like a lot of room to maneuver with all our large context models. And here are the results. So we did this for about 100 different prompts that we generated. And then we looked at the generated SQL and evaluated whether it was correct. At our scale, most of our evaluations we could just verify manually. But we looked at the query. If the query matched exactly, then trivially it was correct. If the result set matched, then it was correct. Then we also asked GPT-4 if the queries were equivalent. So we used plenty of metrics, did some manual inspection, and yeah. So these are the results for all the models that we tested. I hope this is visible, but so turns out GPT-4 is the best performer on this benchmark with an accuracy of about 88%. So it got 88 of the 100 SQL queries right. That's closely followed by three other models. The Code Llama 34 billion instruct, which is not surprising because it is trained to produce code. The Claude V2 and the Claude Instant models, which all had an accuracy of about 85%. So this turned out to be a pretty easy benchmark. So easy, in fact, that some models, like Llama 70 billion chat, for instance, not only correctly answered the request that we gave it, it generated its own requests and then answered them too. So that was interesting. That was the first benchmark. It's pretty easy. The second benchmark was incident summarization. I think I saw a poster of some similar work yesterday. So yeah, we think that LLMs are pretty good at looking at unstructured data and sort of organizing it into a more human readable format when given a template. So they're great for when you have like a whole bunch of code or like JSON data, and then you want to filter out all the noise. That's what we have in some of our socks. We have a lot of alerts. We have a lot of detectors going through user data and generating detections, generating alerts, and we have unstructured JSON data that would be a huge cognitive load for some of our threat analysts to like sift through to find relevant data and actually like investigate threats. So the benchmark is basically we are providing the large language model with unstructured detection data, and then we're giving it a template of how it's supposed to organize this and produce a human readable output. So the template has several sections. Starts off with a summary, which is a 1 to 2 sentence description of what happened. We ask the model to extract observed MITRE techniques from the data, list any impacted hosts, list any users that were involved, and then provide a 1-sentence description for every important event that it sees within the data. And then finally, extract a lot of important artifacts that were involved, like files or command lines, and some details about them. Like, for example, if the command lines were encoded, then we asked the large language model if it could provide a decoded version as well. So evaluating summaries is kind of a difficult problem, especially evaluating them quantitatively. So we came up with a slew of 5 different metrics to try and make sense of which descriptions were doing better. 3 of them are commonly used metrics in NLP. There's BERT score, there's cosine similarity of ADA2 embeddings, and the Meteor score. But then we also came up with 2 other metrics for specifically geared towards summarization. Basically, most of our sections, the where we're extracting information, they're all factual information. So the first two metrics are evaluating how well we are extracting that factual information. So for example, if we want to extract a file path, then we're computing the longest common subsequence and the Levenshtein distance between the extracted file path and what is actually in the data. So here's what the actual results look like for some of the models. I have excluded some of the lower performers because it just became too noisy. But here you can see that GPT-4 performs pretty well on all these metrics, closely followed by Claude V2. And some models don't do really well on pretty much any metric. And it also reflects in the descriptions they generate, which I will get to. Like for example, Code Llama, I guess, is like really good at generating code as demonstrated in the first benchmark, but doesn't do so well here. Numbers can unfortunately tell us only so much here. So I have a few examples for you. So on the top of every one of the 5 following slides, we have the expected description, or at least a section of it, that we want to see from a large language model. So we have the summary section and the observed MITRE techniques. I can't show you the other sections because customer data. And the bottom half has the corresponding sections that were generated by the large language model. So here, the bottom half has the description that GPT-4 generated, and it's pretty good. Like looking at it, it's extracting all the important information in the summary, and it's extracting all the right MITRE techniques. So yeah, perfect score. Maybe it's a little more verbose than necessary when it's generating the summary, but it's pretty good. And then this is what Llama 70 billion generated. It's pretty similar to the GPT-4 performance. It's a pretty good summary. If I would have one nitpick, it's that it missed a small fact in the summary that an account was locked out during this particular incident. But otherwise, it extracts all the MITRE techniques. It does everything pretty well. Here's what J2 Ultra produced. So here, the summary is actually really concise and on point. It's pretty much perfect. But it kind of messes up when it comes to observed MITRE techniques. It repeats one of them thrice and completely misses the other one. Yeah, so it's like not ideal, but still pretty good, still workable. Here's what MPT30B instruct generates. So this is literally everything that the model generated, despite being given a template. It did not follow the template. It just generated a 2-sentence summary with all the artifacts included in the summary, and that's it. It just stopped generating text. So yeah, I mean, although most of this information is correct, it's still less usable than what we expected. And then there's Code Llama, which just regurgitates detection data. And yeah, that's completely useless. You know, it's like, what's the point of spending all that money deploying a large language model? Okay, so that was the second benchmark. And now the third benchmark was basically a harder version of the classic cybersecurity problem, which is we have a ton of data, we have a ton of artifacts. Tell me if it's good or bad. So in this task, we are providing the large language model with the same set of detections that it had in the previous task, but with different instructions. So it's supposed to evaluate the data for how severe the potential incident is out of 5 different levels. So there's critical, high, medium, low, and informational. And in the prompt, we provide the model with the exact criteria for what makes an incident critical or high, or yeah, so on. Turns out, none of the models do very well on this benchmark. They're all just terrible. In a 5-class classification problem, which essentially is what this is, none of them cross 30% accuracy, to the point where we are not sure if they're just guessing randomly. We tried this out in several different settings to see if it would improve things. So the blue bar here is a 0-shot setting. The yellow bar here is a 3-shot setting with the nearest neighbors of the incident that we were looking at. And the green bar is just a baseline, which looked at just two different factors, like an initial severity that the sensor that detected the incident itself assigned, and also the type of the detection. So yeah, and then finally, the only thing that seemed to work was when we just extracted the embeddings of all the data that we had, and then trained an XGBoost classifier on it. It was marginally better. You get a 50% accuracy, but I have the confusion matrices in the appendix, and the balanced accuracy is not that much higher. So those were the aggregated results. Here are some of the failure modes. This is an example of how there are limitations to how much you can engineer your prompts. In our prompt, we had 3 different places where we told the model that it has to follow a specific format. It cannot deviate from the specified format. It can't say anything else. It literally has to produce that JSON. Sometimes it would just produce that exact JSON with XXX. And sometimes no brownie points for guessing which model this is. It produced code to generate the severity. Sometimes they would make up their own instructions. Sometimes they would just regurgitate the data that was given to them. So yeah, putting everything that I've talked about so far together, what we've seen out of our 3 benchmarks is that the large models, the GPT-4s, the Claude V2s, they do pretty well on most of the benchmarks. Let's just not count this for now. And there are some models that are specifically trained to do certain tasks, like Code Llama 34 billion instruct, which does pretty well on the natural language interface benchmark. So what do we know then from this talk about the cybersecurity capabilities of large language models? Well, if you want a threat hunting assistant that can shave off some valuable seconds for your threat analyst, you've got one right now. A little bit of prompt engineering, and you're probably there. I mean, I guess I have to reiterate here, make sure you're like building the right guardrails around it. And yeah. But if you want a model that summarizes unstructured data and sort of helps your analyst that way in the SOC, then you will get, there are models that do pretty well. It won't be perfect. And maybe fine tuning is one way to go to get better performance out of that task. But however, if you want a model that can tell you that whether something is good or bad, something good or bad is happening, and you just want to deploy an LLM out of the box to do this, you're out of luck. There's nothing so far. Hopefully there'll be an LLM in the future that someone in this room might train that on like security specific data, and we'll get there. But yeah, right now, probably a good intermediate solution is to just use embeddings generated from unstructured data and train a supervised model on it. And that's my talk. Thanks, everyone. Any questions? No.
Hi, thanks. Great talk. I was wondering if you had to expand to like 5 benchmarks, what would be like 2 more you'd add?
That's a good question. um, Honestly, right off the top of my head, nothing comes to mind. Yeah, I think we've covered it. Sorry, yeah, nothing is. Yeah, I'm blanking.
If you had to come up with 30 criteria, did you do any just like vibe checks where like you handed some of these outputs to analysts and be like, would you as an analyst be willing to put your career on the line for this, like for a customer that's having their bad day, like just like a vibes-based analysis?
So the summarization problem, the ideal descriptions that I've talked about, those were pretty much reviewed by our analysts for like what facts or what parts of the summary that the model was missing. And then, yeah, apart from that, we just did a lot of manual checks ourselves to see if, some of these problems, we were very aware that the metrics didn't show us the full picture. So we just made sure we were looking at the actual outputs, which is why I have some of my like amazing examples.
I had a question.
Yeah.
About for the threat hunting task, what if you were using a different query language than SQL, or if the queries got a little more complicated, do you test with any of that?
No, that was almost a toy problem because it was like using synthetic data. We limited our scope to SQL.
Hi, yeah, thanks for the talk. I was just curious if you're interested in open sourcing the data.
This is a conversation that we're having internally. There are issues, especially for the second and third benchmark, because it involves real world data. But we've had conversations internally about how this would be a lot more useful if like other people would be able to benchmark their own models against like what we've done. But yeah, no promises. But yeah, we're having conversations about it internally.
Yeah, definitely. That'll be really cool. Thanks.
Great work, Adarsh. Two questions. The first one being, did you notice any problems when you were trying to benchmark any of these large language models on where the model itself did not like generate complete data and instead just like stopped somewhere in between? And the other question would be, for the incident summarization use case, after the model created the summary, did you ever try giving that summary as the input to see what kind of incident it generated?
I'll answer your second question first. Yeah, that does sound like a fun thing to try. We didn't. But yeah, to your first question. Sorry, what was your first question again?
Sorry, the first question was, a lot of these models have input and output token limits. So did you ever run into a situation where, given a context and given a prompt, you ran into a specific case where the model would kind of abruptly stop generating output, especially in the incident summarization case?
Oh, right. Yeah, good question. We were very cognizant of token size limits, especially for the summarization case, because the smallest models we were working with were like 4K tokens. And sometimes we had to actually trim our inputs to make sure we had enough space for the outputs. But yeah, there were a lot of cases where the models stopped generating inputs. It happened more in the third benchmark than the second one, where sometimes it was just the model, instead of like giving us a severity level, would just give us a \n character. I think part of it was just that it wasn't capable of doing that. Like if we were just asking too much of the model, or like it was getting confused. Yeah, but in the second case, we did we also did some like testing. So whenever we were trying a new model, we tried different like temperature settings, different hyperparameters to make sure that the model was performing its best and giving us the best possible descriptions.
So great talk. I'm kind of curious if you could give us a couple more details about how it is you were evaluating the summarization. I know it's like a really thorny problem, like you mentioned. And you had a very specific set of instructions in the prompt for many things that the model needed to do to produce a correct summary.
Right.
And you were doing, I think, LCS to try and figure out if it had missed like a file path or command line. Did you try looking for like, did each of the 5 things show up if they were, you knew they were there? Were there cases like qualitatively where the model got 3 of the instructions right, but forgot to do the last part, or like missed an important fact? Like, and how do you measure that stuff?
Oh yeah, there were plenty of cases where the model got it partially right, especially some of the smaller models. But yeah, and I think unfortunately we also wanted like a single number for each model to compare. I mean, we did look at it manually and sort of get an idea of how the models were doing compared to each other. But yeah, so to answer your artifact evaluation question, so basically the one number we have on the slide here is literally like an average. So we compute the LCS and the Levenstein distance for like one fact, so like one file path or one command line, and then we average it across like all the facts available in that incident, and then average it across all incidents in that we were looking at, and get one number for the model. So yeah, that's exactly why I kind of mentioned that the metrics weren't giving us the full picture, because yeah, again, it's like it's useful for comparison, but yeah, there's a lot more subtlety there that we need to look at manually. Yeah, cool.
In your opinion, were the metrics like with the models that you tested, like kind of finicky, or were they very robust? Like, for example, do you think if you did prompt compression techniques that the same model rankings would come out and they would do about the same sort of level of efficacy as you experienced?
So what do you mean by prompt compression techniques?
Just like asking the model to compress the prompt into a smaller one and then submitting that prompt as the one that you're actually measuring against, or things like that, to get around some of the things like the token limits that other people are asking and things like that.
Right. Yeah, that's a good idea. That's something that we haven't tried. We've tried to look at just like using our expertise with the data to sort of like compress the detections, keep only the important parts of the detections, and I don't know, like try YAML instead of JSON, stuff like that. And I think we were able to work around most of our token size limitations that way. So we stopped optimizing for that. Does that answer your question? Or I think there was a first part.
Yeah, the first part was more on like the robustness of the metrics. So like if you changed the prompt, slightly or something like that, like, would that affect majorly the rankings of the models and things there?
No, I think with summarization, there wouldn't be that much of a difference. But yeah, I would say like this was pretty expensive as well. So we didn't try with a whole bunch of different prompts.
Well, let's thank our speaker for both a great talk and a top 10 place.